Welcome back, everyone. This is Professor Herring. In this video, we're going to continue our discussion about gases. We're going to learn about Dalton's Law of partial pressure. We're going to talk about real gases and what gives rise to them. And then we're going to finish up by talking about the atmosphere. Let's begin. In the most recent video, we talked about the ideal gas law and how ideal gases are gases that behave as though the particles themselves do not take up space and there's no intermolecular forces between them. Because of this, when gases behave ideally, they also behave independently of each other. In other words, if you have two gases in a single chamber, then we can talk about them behaving as individual gases. Let's say that it's hydrogen and helium. We can quantify the number of moles, we can quantify the pressure that each one of them exerts on the container. And that's what we call the partial pressure. Dalton's law of partial pressure states that the total sum of the partial pressures, or the sum of the partial pressures, will equal the total pressure inside the container. In other words, we could simply, if we knew that the pressure of the hydrogen particles and the pressure of the helium particles, we can sum them together, and that gets us the total pressure. This also allows us to talk about what we call the mole fraction. And the mole fraction of a gas is its fraction of the total. And this is true both in terms of pressure and in terms of moles. So looking at the gas particles illustrated here in the box, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 helium atoms. And I'm not going to spend our time counting up the hydrogen, but let's just assume that there are 30. If we wanted to find the mole fraction of helium, it's simply going to be the number of helium atoms over the total, which is 11 over 41. We would do a similar process when determining the mole fraction of the hydrogen. Instead, it would be 30 atoms in the numerator and 41 in the denominator. And so, because the number of particles is proportional to the pressure, and the mole fraction is the ratio of either the pressure or the particles, the partial pressure of each gas is proportional to its mole fraction in the mixture. And all of this comes into effect because the gases do not exert intermolecular forces on each other. If they did, then they would interact with each other and they would not exert the same pressure. They would energy would be lost, and so the pressure would end up being lower than otherwise. So let's practice this. What type of a problem might you see that involves this? So we have a container that contains 5 different gases, and we want to know what's the partial pressure of oxygen within the vessel. You're told the total pressure, the temperature, the volume, and then the mole fractions of each of the different substances. Well, we know that the partial pressure is equal to the mole fraction times the total. Again, this is just saying that all of the different gases, when combined together, provide the total pressure within the system. We also know that the mole fractions have to add up to be 1. And the reason for this is because in the denominator of each of these, it's the total number of moles. And since if we were to solve for each individual mole fraction, we would see that they would add up to be a value of 1. So when we know that, we can calculate the mole fraction of oxygen by substituting in the values for the other 4 gases. Doing this gets us a mole fraction of 0.100 for oxygen. Or in other words, oxygen makes up 10% of the total. That's both in terms of moles and in terms of pressure. So to find the partial pressure, we multiply that mole fraction by the total and get 75.6 torr. Now, this raises an important question. What if we wanted to find the volume occupied by oxygen? Would that be equal to 0.100 times 5 liters? Pause the video and think about this, and then come back and let's discuss. Welcome back. So there's this question of, is there such thing as a partial volume? And the answer to that is no. Each gas occupies the total volume. And the reason for this is because let's say that we have a little hole and we're injecting gases into it. The gas particle is going to spread. We talked about effusion and diffusion. Excuse me. It's going to spread throughout our container to occupy the entire volume. That allows excuse me, that's due to the postulates of the kinetic molecular theory stating that the molecules are going to move in constant random motion. And so just by the statistical, over time, due to the random nature of the gas particles, they're going to occupy the entirety of their container. And since we say that the gas molecules themselves occupy essentially no volume, we can think of, if we introduce a second gas into there, that those particles are also going to simply spread around and occupy the entirety of their container. Another way you can think of this is that if this were not true, we might say that the gas particles occupy certain regions. And so maybe your oxygen's here, your nitrogen is here, your helium is here, etc. Well, if that's the case, then people could only breathe in one area of the room. So the fact that there's oxygen spread throughout means that we can live anywhere within the room. Okay, I'd like you to pause the video and try to solve this one on your own, and then I'll walk you through how to do it. Welcome back. So we have 1 gram each of neon and helium in a 50 milliliter vessel at 25 degrees Celsius. We want to know what's the partial pressure of helium. We use the ideal gas law for this. Something that many students mistakenly think is that you just plug in any random pressure and any random moles here. But in reality, these are linked. Either you're going to have partial pressure, and that's if you have just one substance, or you're going to have the total pressure, and that's if you're using all of the moles. So depending on what information you're given or trying to find, you would use one versus the other. But if we rearrange this, we can then solve for the pressure of the helium if we know how many moles, the volume, and the temperature. The moles of helium let's move this out of the way. It's going to be equal to the mass divided by the molar mass, which is just about 1/4 of a mole. We convert our temperature from Celsius to Kelvin, and our volume from milliliters to liters. We can then plug all those values in and solve for the pressure, which is approximately 120 atmospheres. Let's now talk about real gases. Real gases deviate from ideal behavior. And the reason for this is because in reality, gas particles actually do occupy volume. And in reality, they do exhibit some intermolecular forces. And depending on the experimental conditions in which we're testing these phenomenon, we can observe differences from the ideal behavior. And those two conditions deal with the pressure and deal with the temperature. So at very high pressures and or very low temperatures, then these assumptions break down. And as I mentioned, we assume that the molecules are small and the volume of the container is much, much larger than that of the molecules. Well, that's not true. Molecules do have a measurable size, and at high pressure, that's going to be affected. We also again said that molecules do not attract or repel each other, but that is not true. They actually do attract or repel each other depending on the orientation of the distance of those molecules. So at very high pressures, the second postulate is not true. At high pressures, we're going to compress our gas, and the volume of the container is not going to be as large, and therefore the volume that the molecules themselves occupy is going to be significant. If we were to plot PV over nRT, then for an ideal gas, it should be equal to 1. And what we see is that at low temperatures, from about 0 to 10 or so, that most gases actually behave that. But at high pressures, atmospheres in the 20s and the hundreds, those gases deviate significantly from the ideal behavior. What you need to recognize is not which gas deviates in what way. Does it go down and then up, or does it just go straight up? But rather recognizing what are the factors that are going to come into play. And essentially what you want to do is think about which of those gases are going to have the highest intermolecular forces. Because the highest intermolecular forces means that it's going to have the highest deviation from the ideal. At low temperatures, we also get deviation. And the third postulate states that the molecules do not exert attractive intermolecular forces. High pressures and low temperatures, this is not the case. And the reason for this is because as the pressure increases, the molecules are closer to each other. Therefore, they have more opportunities to interact. And as the temperature decreases, the molecules don't have enough kinetic energy to overcome the attractions. When we introduced at the beginning of chapter 11, we talked about how gases, their kinetic energy is much, much higher. Let's try this again. If we're comparing intermolecular forces to kinetic energy, that for gases, the kinetic energy is much, much higher. For liquids, they're roughly equal. And for solids, the intermolecular forces are much, much higher than the kinetic energy. And so because we're decreasing the kinetic energy as we decrease the temperature, there's not enough energy to overcome the intermolecular forces, and they behave much more similarly to a liquid than they do a gas. What we see is that different gases will deviate from the ideal gas law differently. And then under the same conditions, those with the strongest intermolecular forces will deviate the most. And we mentioned this already. So let's see if you understand this. Go ahead and try this question on your own. Pause the video now, read over, and answer it, and then I'll walk you through the logic. Welcome back. So we want to know under which set of conditions would the ideal gas most accurately describe the behavior of a gas. What we know is that the deviation from ideal behavior happens at low temperatures and high pressures. This is, again, the deviation. Therefore, and also gases with strong IMFs deviate more. So if we want to know under what conditions is it most accurate, we want essentially molecules that are going to have no IMFs, and we want there to be high temperature and low pressure. Okay, let's move on to talk about the atmosphere now. The atmosphere is made up of about a dozen or so different gases. And this is at sea level. This is dry air. So you'll notice that there's no water represented there in the air. The fraction of water is going to depend on the relative humidity. And one way to express the content is by using the mole fraction. Remember how we said that the sum of the mole fractions must add up to be 1. And what we can see is that the vast majority, about 78% of the air, is made up of nitrogen, and just under 21% is oxygen. Below that, there's then less than 1% of argon, and even less than that of carbon dioxide, neon, helium, etc. And so these percentages roughly stay the same at sea level, although there's been a lot of talk in the past few decades about carbon dioxide emissions and other compounds. Nitrous oxide is made from when fossil fuels are burned in complete combustion. And so these, especially carbon dioxide and methane, those are particularly troublesome because they're what we call greenhouse gases. And greenhouse gases, they trap in heat that gets emitted from the sun, it reflects off the earth, and then gets trapped in, kind of like a blanket. And this is actually a very good thing. We want to have the greenhouse effect. If we didn't have it, then everything would actually be frozen over and the earth would be inhospitable. So we need to maintain a proper balance between trapping in heat and letting heat out. And that's why this issue of levels of greenhouse gases is important. Because if we have too many greenhouse gases, then that's going to increase the temperature too much and make it too hot for living conditions. But if we don't have enough greenhouse gases, then we would freeze. And so part of our life here on Earth is to help maintain it and to help try and make sure that we are living within balance. So that way we can have the best living conditions possible. So as I mentioned, we use the mole fraction to describe the content, the percentage, if you will, of the different components. But we can also talk about them in terms of parts per million, parts per billion, and parts per trillion. And the reason we would do this is because when you look at the mole fractions of things such as carbon dioxide and neon and helium, it's very, very, very small. And so by converting it into parts per million, billion, or trillion, it brings it up to a scale that's a little bit more comprehensible for us. So for example, if you wanted to calculate the concentration of nitrous oxide in parts per million, you would take the mole fraction and multiply it by that factor, 10 to the 6. That means then that there's 0.325 ppm, or parts per million, of nitrous oxide. As I mentioned before, the atmosphere is made up of a variety of different components, and the atmosphere itself is very complex. The exact pressure that you would experience is going to be dependent on a variety of different factors. We can see here that the pressure, here in green, is a function of the altitude. And the higher the altitude, the lower the pressure. We see that temperature fluctuates over the course of the height of the atmosphere. And that we have this oscillating pattern where it gets colder and then hotter and then colder and then hotter again. And the density of air also tends to trend with the pressure. But what we see here is that different amounts or different types of light are absorbed or will go through our atmosphere. So very high energy UV light only makes it here through the thermosphere. Medium length UV light is going to make it all the way down to the stratosphere and gets taken up by the ozone layer. And then the lower energy wavelengths, this is getting into the visible region, slightly into the UV region, makes it all the way down to surface level. And that's the energy that ends up heating our planet. So that's it for this video. Thanks for watching. If you do have questions, ask on Piazza in office hours or recitation. Have a good day.